Welcome everyone, my name is Barrie Kersbergen. I'm a data scientist working at bol.com, where I've been working on the recommender systems for the past 12 years, and I'm also an external PhD candidate at the University of Amsterdam. I present work done on serving low-latency session-based recommendations at bol.com, together with Olivier Sprangers and Sebastian Schelter. Bol.com is the largest online retail platform in the Netherlands and Belgium. The platform serves over 12.6 million customers and offers over 33 million distinct products over a wide variety of categories. Bol.com has over 7,000 pickup points in the Netherlands and Belgium, and more than 47,000 retailers are selling products on the platform. Session-based recommendations, abbreviated as SBR, targets a core scenario in online retail, where the goal is to predict the next item or set of items that a user will interact with in a short period of time, which is called a session. So let's say that someone is looking at several LEGO Mindstorms related products, such as in the left image, and the question is what is relevant to show to that customer. And an example where these recommendations are shown is on the product detail page of the bol.com website, as you can see in the right image. From a mathematical perspective, given a sequence of chronologically ordered tuple item click events at time t, we must present the next item the user will interact with at time t+1. Using session-based recommendations with millions of distinct items, such as our real-world use case at bol.com, is challenging from a computational perspective because the input space, the sequence of the item interactions for the recommender system, is exponentially large, which renders it impractical to pre-compute these recommendations offline and then serve them from a data store. So instead, these session-based recommendations have to react to the changes in evolving user sessions and then compute the next item recommendations online. These predictions have to happen with low latency, as there are strict service level agreements for response latency and throughput. At bol.com, we must adhere to a max of 50 milliseconds and handle at least 1,000 predictions per second. Now, from an algorithmic perspective, the used data sets are high dimensional and very sparse, containing millions of items. Often, the real-world data sets are orders of magnitude larger than public academic data sets. Scaling these session-based recommender algorithms using embeddings would require to rank all the items, and then for k-nearest neighbor-based approaches, you would have to go through hundreds of millions of historical sessions in the training data. So we wanted to improve our others also viewed recommendations on the product detail page of bol.com using the algorithms from the Rexis community that give high-quality recommendations and then find out how efficient they are. So we replicated this study from the Rexis community on a sample of our own proprietary production data at bol.com. We confirmed the findings from this study that the simple nearest neighbor based approach VSKNN outperforms other methods such as neural network based methods in session-based recommendations on e-commerce data, as can be seen in this figure, both in the prediction quality, the mean reciprocal rank, and the inference time P90. We additionally found that VSKNN is orders of magnitude faster to train than neural network-based methods. And this is an important property for a production system that has to conduct regular retraining of models and adhere to strict time constraints for that. We published our work on this subject at the ICD 21, Learnings from a Retail Recommender Systems on Billions of Interactions. And to the best of our knowledge, there exists no scalable production-ready recommender system employing the k-nearest neighbor-based recommendations for session-based recommendations, despite the superior performance of the approach in academic studies. So therefore, we worked on the design and the implementation of a scalable implementation of VSKNN called VMIS-KNN. Let me start by explaining in a simplified manner the VSKNN algorithm and then introduce the modifications we made to speed it up. The nearest neighbor-based approach computes the next item recommendations for an evolving user session based on the historical training sessions from click logs in 4 steps. First, it finds all the historical sessions that share at least one item with the evolving session, and then it retains the m most recent historical sessions from the matches, and then it computes the similarity between the evolving session and the matches via a weighted aggregation on the positions of the shared items. And then it scores the items k for the most similar sessions. Our algorithm VMIS-KNN, which stands for Vector Multiplication Indexed Session K-Nearest Neighbor, is an adaptation of VSKNN that enables low latency predictions. So the core idea of our algorithm is that we pre-compute a data structure, an index, with the m most recent historical sessions for every item during training. And then for each item, we also sort the entries, the sessions, by timestamp. When doing online predictions, we jointly execute steps 1, 2, and 3 based on this pre-computed index. The result is that the worst-case time complexity, assuming that we have a fixed constant number of items per historical session of the operations during inference for these steps, is now reduced from big O, the length of the evolving session, times the number of historical training sessions, to the big O, the length of evolving session, times the recency sample size, because the index only needs to retain the recent samples for every item in the evolving sessions instead of the theoretical all historical sessions that could contain an item. And this reduces the worst-case performance of our algorithm to a constant depending on the recency sample and thus independent of the number of historical training sessions. To validate the design choices for the algorithm and the index data structure choices, we implemented 3 algorithms in Rust. The original VSKNN algorithm, but then programmed in Rust, VMIS-KNN no optimizations, as explained in the previous slides, and VSKNN, which also contains optimizations. So one of the optimizations is that we can maintain a small intermediate results on the recency sample size for only a small amount of memory during the computation. And then we incrementally compute the similarity for those recent sessions only by performing early stopping, which allows us to skip all the historical sessions during the similarity computation. We also prune the index from sessions with 2 odd timestamps, and sorting the sessions by timestamp in the index allows us to do early stopping once we come across a timestamp that is smaller than our current minimal timestamp of our recently sampled sessions. This version also leverages octernary heaps instead of binary heaps, which have more children per node, and therefore provide better performance on workloads like ours with frequent insertions. We verified these modifications in a micro benchmark, which you can see in the figure. We confirmed the theoretical improvement of the time complexity, where we see the better, worst, and average time complexity, and this is an important property for our online setting, so we can guarantee low latencies with a P99 less than 10 milliseconds. To validate our implementation, we measured the inference performance on different implementations on 6 click datasets. First, the VSKNN in Python from the original paper. We expect this variant to be non-competitive as it's mere a research implementation. And then we also compared differential data flow, which computes the recommendations incrementally via joins and aggregations. And this allows us to evaluate the benefits of having an incremental similarity computation for the growing sessions. Also a Java implementation, which stores the historical session data in Java hash maps. And then the purpose of this variant is to evaluate the effects of not having full control over memory management during the similarity computation and instead rely on a garbage collector. And fourth is our optimized Rust implementation. And then we benchmark the performance by exposing them to the historical training data from public and proprietary datasets, and then using a test set, we ask each implementation to sequentially compute the next item recommendations in a single thread for the growing evolving sessions, and then we measure the prediction time in microseconds. We run each implementation on a HiMem8 instance in the Google Cloud with 50 gigabytes of memory. And then the figure illustrates the resulting runtimes from the experiment. And then we plot the median and the 90th percentile of these runtimes on a logarithmic scale in a single bar, where the lighter top part denotes the 90th percentile runtime. The VMIS-KNN implementation consistently outperforms all the baselines in terms of the median and the 90th percentile runtime. Also, our 90th percentile is less than 1.7 milliseconds on all datasets, which we attribute to the fact that our implementation allows us to carefully control the memory allocation and thus avoid the materialization of large intermediate results and not having to keep track of the full catalog ranking for one request. Our VMIS-KNN is also an order of magnitude faster than all the other baselines, and when we look at the larger datasets, we additionally observe that several baselines start to encounter memory issues and start to fail the computation, as happened for Python, which relates on Panda data frames internally, and the Java variant. So we now have an efficient implementation of the algorithm, but how do we design an end-to-end recommender system around it? We will now give an overview of the architecture of our recommender system called Serenade, as illustrated in this figure, which consists of 2 components. The offline computation of our session similarity index is leveraged on Apache PySpark job. that generates this index in a regular time interval, typically once per day in Google Dataproc, and then it uses the historical data for the last 180 days of our platform stored in Google BigQuery as input, which amounts to roughly 2.3 billion user item interactions as training data. The second component is the online computation of the next item recommendation with famous KNN in response to the session updates. And the pre-computed session index requires around 13 gigabytes of memory per serving machine, and then we replicate our index to all the recommended services. In long-running load tests, we observed that Serenade can easily handle 1,000 predictions per second, and it only needs 2 vCPUs in total to compute this. We must keep track of the evolving user sessions and then store these items in a local key value store, for which we use RocksDB. The communication with RocksDB is very fast. In the micro benchmark, the 99th percentile for the write latency was 18 microseconds for a workload with up to 10 million operations. For the co-location, we must partition both the evolving session and the recommendation request, which also contains the session updates, over the serving machines, and we do this based on the session identifier, and then we configure the request routing via sticky sessions provided by Kubernetes Session Affinity functionality. We're also required to provide non-personalized recommendations for users who do not give consent to leverage their session for personalization. And this can be done very efficiently, as each request from the shop frontend includes a binary flag denoting the status of the user consent. And then we return a non-personalized variant, which only leverages the current display item on the product detail page for recommendations. So does the strong online performance of session-based recommendations also translate to strong online performance? Because in the end, the recommender system has to perform well in business-relevant metrics to be valuable for an e-commerce platform. So we run a large-scale online A/B test on the live platform of Bol.com, where 50% of the visitors receive recommendation from a legacy item-to-item collaborative filtering system, and the other 50% of the visitors receive recommendations from Serenade. This A/B test ran for 3 weeks, and the recommendations were shown on the others also viewed slot on the product detail page. We're interested in knowing if the difference in the conversion-related business metric, but also the engagement from customers with the recommendations on the product detail page. This A/B test included 45 million user sessions, and we found that Serenade easily handles the load up to 600 requests per second, which happened during the A/B test. The response latency for the prediction was less than 10 milliseconds at the 99.5 percentile, and this is way beyond the response times that we see for existing systems. So we found a significant increase of almost 3% in conversion-related business metric compared to legacy. We would like to highlight that, to the best of our knowledge, we're the first to provide empirical evidence that the superior offline performance of famous KNN also translates to superior performance in terms of business metrics in a live, real-world recommender system. And this is not always the case for academic recommender approaches. For example, the winning solution for the highly popularized Netflix prize but never went into production. With that, I want to come to an end to the presentation. We have presented the design and the implementation of our scalable session-based recommender system Serenade, which employs a scalable implementation of VSKNN called famous KNN. Go check out our paper for details and additional experiments. Serenade is deployed and in production at Bol.com, the largest online retailer in the Netherlands and Belgium, and Serenade supports instant depersonalization if a user withdraws consent for recommendations. We publicly release our code and software on GitHub. Go check it out, and if you're interested in more information about my work, visit my research page, and I'm looking forward to questions and discussions.